Well, welcome to our short lecture series on Thursday, the 19th of November, 2020. This is a series of short 20-minute lectures by guest presenters concentrating on Earth expansion, paleogravity, or related subjects. If anyone has any suggestions for specific lectures, please let me know. The list of planned lectures can be seen at dinox.org/lectures. And today, John Eichler is going to talk about cosmology and geophysics. This talk will delve into the possible link between a cosmological theory and Earth expansion. So it's over to you, John.
Okay. I'm going to talk about cosmology and geophysics and somewhat how I got in with the cosmology and how they are related, because actually the Earth is part of the universe, and so it all kind of fits in. First of all, you're familiar with Occam's razor, which says this rule is interpreted to mean the simplest of two or more competing theories is preferable. Because of our interest in expanding Earth, I'm sure that all of you are familiar with the fact that the Earth expansion is something which is the simplest theory to explain the most things, and consequently it's like anything. I mean, the simpler it is, the better it is. An explanation for unknown phenomena should first be attempted in terms of what is already known. In this regard, I regard, well, first of all, let me tell you what I'm going to talk about. I'm going to talk about the development of new concepts in science, the importance of the laws of physics, cosmology, and here I'm going to talk mainly about the gravitational forces versus electromagnetic forces, which come into play with how galaxies are formed and how our solar system actually got formed. And then I'm going to talk briefly about the geophysics and how this expanding Earth fits into how I view it and the uniqueness of Earth. When you're developing a new concept in science, there are a number of areas of science where I think we really don't understand. We think we understand what's going on, but in reality don't. The expansion of the Earth is one of these areas. There are a number, for example, you think of dark matter in the universe, but do we really have dark matter? There's a number of places where we really feel like we know what's going on, but I don't think we do. And one of the reasons for this is that there's no direct hands-on observation beyond what's in our reach. For example, we can't go into the center of the Earth to tell what's down there. The maximum we've gone down is, I believe, is 40,000 feet, and which is only like a thousandth or less of the distance to the inside of the Earth. And at the same time, when you look out in the stars, all you can see is the light coming here. You can analyze the light, but you can't really get out there and do a hands-on observation like you could do in a laboratory. However, we must remember that the strongest evidence for any of these ideas come from where laboratory experimentation backs up the theoretical constructs. And deriving concepts from observations depend very much on how the observations are interpreted by observers. In other words, what their worldview is. And by that, let's see, and when you're doing that, and I'll get to that in a second, but with new things like the expansion of the Earth, dark matter, this type of thing, you can always come up with some type of esoteric type laws. But if you have a law, if somebody comes up and anybody can think up any kind of a theory, but I always question any kind of what I would call new esoteric laws. And we'll get into that a little bit when I talk about the geophysics, because Kerry was one of the ones that was talking. I mean, he threw out several ideas about what's causing Earth expansion, but to me, they were really esoteric. I always question a concept if it does not have laboratory experimentation or experimental verification. You can talk about, I don't know, anything, but unless you can go into the lab and actually produce results to verify what your concept is, I think we should question that type of thing. And just because a concept can be visualized doesn't mean it follows the laws of physics. And I'll give some examples of this. And there is no evidence to suppose that the laws of physics aren't valid everywhere throughout the universe. And in my opinion, known laws of physics must be obeyed. Now, a few words on worldview. Worldview is what scientists bring to the table. This is how the scientist thinks of the universe working around them. Different people have different worldviews. And this is important because our worldview, or whoever is making the observation, affects the observation and their interpretations of the observation. For example, to a hammer, everything looks like a nail. But paradigms, the way you view a particular topic, is a two-edged sword. One, paradigms really assist us in our cognition of the world around us. On the other hand, they hinder us from looking outside the box. In other words, we have to be a little bit careful. Now I'm going to get into cosmology a little bit. First question, is the universe expanding? Well, to figure out whether it's expanding or not, we have to know both the velocity of galaxies and other bodies and the distance. The velocity, if you regard the redshift as an indication of velocity, velocity is relatively easy to determine in that manner, but distance isn't. Now, Hubble wanted to solve the distance problem, and he did this by using a Cepheid variable, which is a variable star. And from the variable star, he could tell, since it was variable and since it was all Cepheid variables were pretty equal in their characteristics, he was able to determine the distance to our nearest galaxy, the Andromeda galaxy. And he came out with his very famous, in his 1929 article, with his very famous drawing here. And it didn't go out very far. It went out to just a few surrounding galaxies, as you can see from the number of points. And he extrapolated and found the best fit of that, and it happened to be a straight line. This fell in very, very nicely with the concept that the universe was expanding, which, by the way, one of the people that came up with that concept in the 1920s was Lemaitre, and he was a Catholic priest. So he always liked to know, because once you know it's expanding, you can always go back to the beginning, and that's how the Big Bang originated and this type of a thing. But the redshift could be caused by two things. The first, most obvious one, is the Doppler effect. And this is, I'm sure that all of you guys are familiar with the Doppler effect, but this is where the velocity of the source of either the source or the observer is, if it's going away from you, you end up with a red shift. If it's going toward you, you end up with a blue shift. Well, this Hubble's diagram was interpreted with the Doppler effect, which proved everybody, oh, gee, the Earth is expanding. But also you can get a redshift because by the loss of energy of photons. The energy of a photon is Planck's constant times the frequency. And the frequency, of course, is the velocity of light over wavelength. So you end up with a wavelength inversely proportional to the energy. So if the energy falls, then the wavelength becomes longer. And consequently, you end up with a red shift. Lower energy results in a longer wavelength. But Hubble, not knowing any physical way that you could drain energy off a photon, always questioned the redshift himself. in other words, he thought that the velocity from the data that was coming in, especially later on when they started looking at more galaxies, he thought the velocity of the galaxies, of distant galaxies, was far too great to be believable. And he never believed in the redshift. Contrary to everybody attributes the expanding universe to Hubble, but Hubble himself never believed it. He always prefaced anything he said, if it is a Doppler effect, then, but he spent, actually, he never thought that the universe was undergoing expansion. And he spent the last 25 years of his life searching for a valid way to determine once and for all that the universe was, in his terms, reasonable and sensible. When I was doing my research for my master's thesis, I ran across a book called Evolution of the Solar System. It just happened to be in the library, university library, and I was interested in looking at some things from the cosmological standpoint. And there was a fellow by the name of Hannes Alfvén. Now, Alfvén was from Sweden, and he was known as the father of plasma physics. Now, in my humble view, Alfvén is one of the people of our last century, one of the greatest minds of our last century. And he got into physics. He lived in Sweden. They saw the Northern Lights. He was very interested in this type of thing. He became a professor of engineering, electrical engineering. And interesting thing about Alfvén was that he is one of the few people that belonged to both the American and Soviet academies of science, very highly regarded. He was an experimental physicist. He knew theory, but he always insisted that it be based on experiments that he could do. And any scaling he would do, he would base all his scaling on things that he could experimentally verify that the scaling was proper. And he did a whole bunch of things. In the three books, this 1942 book, which is actually, I don't know, 40 pages long or something like that. It was a very thin one. And then he was beginning to think about how the solar system and how the universe is put together. In 54, on the origin of the solar system was his second book. And then he went on, and he was always interested in this idea of how galaxies form, how the solar system forms, how basically everything forms. And this culminated, I mean, this is only a partial list of everything that he got a Nobel Prize in 1970. He and a fellow by the name of Aramis worked for 7 years, consulted with NASA, and came out with this book about the evolution of the solar system, which I think is almost a must read. It really is interesting. And he gets into the shaping of our universe. And because because electromagnetic forces can be stronger than gravitational forces, he always questioned the standard view that our universe was created by gravity alone. He said that it should be electromagnetic forces. And the current paradigm is the gravity shapes the galaxies, the stellar bodies like our sun, and solar system like the planets we have. Alfvén's paradigm, in other words, his worldview is electromagnetic forces shape the universe, enormous plasma currents flow in space. And plasma is simply the ionized gas, but you end up with lots of electrons and ions flowing in free space. The plasma currents don't need a conductive media. Up to this time, it had always thought, everybody said, no, there's no current in space. They always thought that it needed something like a copper wire or some type of media for current to flow over. But Alfvén said no. And one of the interesting things is that the mechanism that he came up with, now this is to me, he's a noted physicist. He's basically, I mean, we end up being a physicist, you ensure that what you're talking about has a solid foundation. And Alfvén said the same mechanism for planets and that formed planets also formed satellites. Okay, plasma currents in space. Nobody thought this was really possible. Alfvén hypothesized plasma currents in free space. What happened was when they sent up space vehicles, they began to pick up these currents. Sometimes the satellite or whatever the probe was would go through and have very little, detect very little electrical field. And then all of a sudden you get into thousands of volts. And this concept of plasmas in space is one of the basic concepts that Alfvén had when he was working. These currents can produce very large electromagnetic fields. And the computer simulations that were later done, and Alfvén knew that because of his experimentation with plasmas, he knew how you could scale these and actually scale them. And Stephen, you probably know from the standpoint of scaling, how you scaled up. There's certain criteria that you can scale from the standpoint of the size of the dinosaurs and this type of thing. Well, you have to follow certain rules. I mean, if you don't, the things don't scale properly. Alfvén knew this. And the computer simulations done by Tony Peratt, they used currents. They did on supercomputers, and they used currents 10 million trillion amps. And these currents, the flow, if you could imagine this huge wire, or I mean, it's huge, and 300,000 light years apart. When such currents interact, they can form galaxies. And once again, these are done as scaled extrapolations based on laboratory experimentation. To show how that works, this Eric Lerner, by the way, wrote a book that you might be familiar with, The Big Bang Never Happened. And he goes into this electrical thing. And what happens is you end up with two electrical currents. By the way, Stephen, can you see my cursor okay? Yes?
Yeah, we can see it fine.
Okay, fine. So what you end up with are these currents, and when they come together, because well, if you have a plasma traveling, the current will try to go to the outside. In other words, one side will become negatively charged and one side will become positively charged. And when they come together, you end up with this looping action. And as you loop down like this, it constricts it, and you end up by forming a galaxy. Now, when they did these computer simulations, these are some of the pictures. Let's see. Okay, here are the two filaments to begin with. They come together, they begin to twist around each other. They twist like this. They twist, 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 twist. And what amazed Peratt when he did this was that he went to ARP's Atlas of Galaxies, and he found, for every one that he found with a computer, he found one that would be almost identical in the Atlas of Galaxies, which lends a lot of credence to this idea. Now, his thing showed very, very large electromagnetic forces and gravity, and you have some gravity because some, I'll get into that a little bit, it's not completely EM forces. But the output shows typical shapes of observed galaxies. Lerner, Eric Lerner is a kind of interesting guy. He's out in New Jersey, and he wrote that book, and he was training to become a PhD theoretical physicist. And then he got off into writing, and he's done a lot of writing, and he stopped his education. But he did some calculations, and because he and Peratt and Alfvén all knew each other, and Lerner did some calculations of spacing of objects, and he found typically stars have a spacing of 10 times a million, 10 million times their diameters, galaxies by 30 times their diameters, and clusters by 10 times their diameter. And these numbers actually he found work out very nicely because they actually explain the different spacing of stars, galaxies, and clusters. And An interesting point that Pratt's computer simulations did, they actually found that the stellar velocities around galaxy centers correspond to what is actually observed, meaning no dark matter is really needed. And to show you what I mean by that, there was a gal by the name of Vera Rubin, who was a very famous astronomer. She died, I believe, earlier this year or the last part of last year. But she studied galaxies. And what she would do is come over here with the galaxy. You have the center. But then on each side going out, she would do a slit observation and calculate or determine the red shift or blue shift, because as the galaxy goes around, of course, on one side you're going to get a red shift with things are going away from you, the stars are going away from you, and the other side you get a blue shift because they're coming toward you. So you can determine their velocity. And she found for like this galaxy 2742, she found as you got away from the center of the galaxy, the velocity went up like this and just kept going. And here's another galaxy. It went up, went down a little bit, kept going. Another one comes up, wavy line. The importance of this is that by gravitation, by the gravitational laws, Kepler's laws, the further away from the center of an object, the slower you need to go. And I'll give you an example of the solar system. Mercury is going around pretty fast. Venus takes a longer time to go around, is slower. Earth is slower than Venus. Mars is slower. By the time you get out to Pluto, it doesn't need a lot of velocity to keep in orbit. Everybody considered galaxies as similar, an analogy to our solar system. Consequently, the further away you get from the center of the galaxy, the slower the object should be. But when you look at a galaxy and take the actual measurements, you don't get this. The only thing which the solution to this, the obvious solution is, gee, the galaxy has more mass. Therefore, Kepler's laws still hold, but it has more mass. And so the whole concept around these measurements is where this dark matter concept came up. And Pratt's simulations of this showed that you get far out, it's going to have the same velocity as further in, because it's electromagnetically driven rather than gravitational driven. And that's why I don't believe that there is such a thing as dark matter. They've been searching for it for how many years now? Well, 30 years, and they never even found it. See, theorists go wild about this. I mean, this is a great thing theoretically, but it's not really that valid. But from the standpoint of the formation of the sun, well, each sun, you can imagine that sun surrounded by a sphere that's 10 million diameters away from that sun. In other words, that's the matter that's affected by that sun. That's the typical spacing of suns. The sparse matter began to do the gravitational collapse. In other words, gravity actually began to pull in particles. And these particles, as they came toward us, that they coagulated at some point, and you begin to get the suns formed. The sun is so large that even a very slow rotation produces a very high angular momentum. And the sun was spinning much faster in the past. And one of the things that's important is, and these were simulations done on a computer, that you have to have some deuterium. Now, deuterium is an isotope of hydrogen, just a hydrogen and a neutron. But you have to have, it only contributes like 1.5%, 2% of the amount of matter coming in. But you have to have this in order to actually find your modeling is correct from the sun. If you don't have it, the sun just peters out pretty fast. But you have, and this is like in millions of years, you have this deuterium burning sun, and you can see that the solar radius is much, much greater than our present sun's is, which you could explain from the standpoint of the a paradox of the early sun being hotter, this type of thing. And from calculations that they had done, here's 200 million years ago and 80 million years ago. During the early geological periods, after the Archean, you could have a very, very hot sun. Now, I want to go into the formation of the solar system, which I really think this is an interesting topic. The sun has a very strong electromagnetic field. As gravitation attracts...
Can I ask a question, John?
Sure.
Can you go back one? That doesn't seem, the time scale seems way off. 200 million years is nothing. I mean, we're talking 4.5 billion years.
I understand that. Let's see.
So what it's suggesting there is that the sun was 16 times larger, or radius was 16 times what it is today, only 200 million years ago. Are you sure it's 10 to the 6 years at the bottom?
Yeah, I got this right out of the publication that was done. This work was I got this publication because Alfvén had referred to it in his work, and they had Alfvén and Aramus had done studies on this. So what I'm doing is I'm grabbing this out of his work, and yeah, I grabbed the figure directly out of the thing.
Okay, it doesn't
now whether it was 120 or 100 million years ago, I agree with you, because the continental split would start to happen about 250 million years ago.
Right.
But here's 10 times the diameter. But once again, I know with Maxwell maintained that there was a time that the sun was much, much hotter than it is now. I mean, and this is why I'm not completely discounting this. I mean, the time thing might be a little bit off, Bill, but I really think that the this is
10 to the 7 years would be what? That would make it 2 billion going back? 2 billion. 10 to the 7 years, if that were the scale. And that is a little better. 10 to the 8th would be 20 billion. That's way too long. I mean, that's longer than presumably the age of the universe. So I just question whether the 10 to the 6th is correct at the bottom.
I'll remind me of that if I forget it, but I'll send you the reference so you can take a look at it yourself.
Okay, thanks.
Okay.
Yep.
Let's see, where was I? Okay, the particles. Okay, now this is an interesting part. If you're imagining this sphere that is 10 million times the diameter of the sun, and particles begin to be attracted because as the sun is growing, the magnetic field is going. But as the particles get attracted, they fall toward this gravitational potential, the sun. And as they fall, they reach a certain critical velocity, because their kinetic energy keeps getting, the potential energy as they're falling gets changed to the kinetic energy. They get faster and faster and faster. And finally, you hit this critical velocity. And when you hit the critical velocity, what happens is that the particles, the actual atoms, begin to ionize, because they're exceeding the force of holding the electron on, and they become ionized. And then the ion, because the sun is an electromagnetic source, the ion is stopped by the sun's line of force. The rotation of the sun attempts to move the particles. I'll show you a diagram of this in just a second. Attempts to move the particle in the same direction the sun is rotating, and this has been shown to happen. The result is that the particles gain some of the momentum the sun loses. In other words, is similar. How would I say it? if you're swinging I was trying to make some kind of analogy. The sun's magnetic pull on these particles increases the particles, and I'm talking about atoms, increases the atom and tries to, like a string pulling on that particle, it starts to move the particles. And as it does this, the sun loses a tiny bit of its momentum. This is important later on. The particles speed up, and then by centrifugal force, and they move downward toward the equatorial orbit around the sun. The result is rings similar to Saturn's rings, but now around the sun. And the rings accrete to become the planets. Now, what happens here is here's the sun is rotating around, and we're looking at a cross section of it. These are particles in falling neutral gas. Finally, they ionize. And when they ionize, now some of them will come down toward the polar regions of the sun. But as they come in and ionize, they get stopped by the lines of force of the sun. Then as the sun continues to rotate around, each of these particle atoms become faster and faster. They have a centrifugal force. And as the centrifugal force comes, they are forced out the same way as if you're swinging a rope around. It tends to go in a horizontal plane. These particles slide down the lines of force to an equatorial plane of the sun, and they form rings, almost like Saturn. And here's once again with the sun, and they form these what Alfvén calls jet streams, and that's how the particles in the jet streams are moving, because they have taken momentum away from the sun. And when the particles come in, this is one of his graphs or charts he made up, and you have a certain ionization potential of the the voltage potential necessary to actually ionize these. And you have helium and hydrogen coming in, and they form a cloud A and cloud B. And then you have these lithium, beryllium, boron, carbon, oxygen. These form a cloud C. And once again, these clouds, if you read in Alfvén's book, there's particles that go through some of these depending on how far the particle was out. And I mean, it gets kind of messed up. And then you have a cloud. So he defined basically 4 clouds, A, B, C, and D. And according to the ionization potentials. Now, these land at different places in our solar system, which contribute to the composition of the planets. And this is another figure that one of his students actually did, and using this concept of how the solar system was formed. You see Mercury, Venus, Earth, and Jupiter formed first, and then you end up with Saturn, Mars, and then over here. But this is based, I have if you're interested, I have a research paper. I think it was this guy's thesis, a PhD thesis that he did, and he was under Alfvén. So what you end up with are these various clouds, A, B, C, and D. And those formed the various planets. Now, because the larger planets, like Saturn and Jupiter, are so large and they're so far away, that almost all the angular momentum in the solar system is in these larger planets out here. Because the sun actually was going faster, and it slowed down the sun, slowed down the angular momentum. But the particles which form like Jupiter and Saturn, this is Neptune and Uranus. They take up most of the momentum, and that's why the momentum is so skewed in the solar system. And then Alfvén did something very interesting. He took the same mechanism applied to satellites. He said, well, you end up over here with Jupiter, and Jupiter has various satellites which correspond to satellites around Saturn, Uranus, Earth, Mars, etc. Now, Mars, he was really questioning whether these were actually captured bodies, the two moons of Mars, because Mars doesn't have as much of a electromagnetic field. But all the planets that end up with satellites have magnetic fields. And so I would refer to Alfvén about the details of this, but he said that the Earth probably had like 5 to 10 satellites to begin with around it. But he bases the same thing. You have an incoming flow of particles. Because these planets have a magnetic field, you end up with the same effect that you do when the sun was forming the planets. And they go into orbits around the planets, taking a little bit of the angular momentum of that, and the satellites form that way. Now, the formation of our moon, there are 4 theories on this. There's what I call the Maxlow theory, which is the Barbell theory. There's the fission theory. There's the Earth orbit accretion theory, and the Earth capture theory. And I'd like to go through these. Now, Stephen, I've gone quite a while now. Should we are we going to get running into time constraints with the with this? Should we go to a different?
No, it's fine.
It's fine. Okay.
Yeah, it should be okay.
Okay, the barbell theory, and this is kind of a poor illustration. This is the only one I can find with 2 spheres attached. But basically, you have 2 blobs of hot material, like the sun material, which broke away from the sun, probably by James thinks is by centrifugal force. I question this, but they were going around, this barbell was going around, and they finally broke off. He ended up with the moon and the Earth. And his basic reasoning behind this is that the composition of the Earth is very much like the composition of the moon. Okay, so you have centrifugal force spun off in a barbell-shaped blob from the sun, which is one of the big problem. They separated to form the Earth and the moon, and there's some problems. They are based on the similarity, or many similarities, between the Earth and the moon from the standpoint of the geology of it. It pushes the laws of orbital mechanics. That's the first thing. You have the 2 blobs. Conceptually, it's nice. But when you get down to try and analyze this, it is real problems. And there's a thing that is called the Roche limit. I don't know whether you've ever heard of this before. Have any of you heard of this before?
And yeah, it's where the moon breaks up if it's too close, isn't it? And
yeah. Whenever you around any body like the Earth, there's a certain distance out, and if an object was to pass through that distance, it would break up. It would pulverize, and this is because of the gravitational forces put on the body compared to what it was. So it's very hard. I mean, this is why you can't say that something just broke off in a big chunk and went out to form the moon. The forces, these forces, gravitational forces, would break it apart. And with other planets, it'd be very problematic. I mean, can you imagine something like this explaining the moons around Jupiter? You know, I don't know. Next theory is the fission theory. And this is the one where you ended up with some Mars-sized body coming in, hitting the Earth, throwing out all this garbage, which coagulated into a ring, which then condensed into the moon. Mars-sized body hit the Earth. And there are some problems with this too. One, where did the other body come from? Now, if you look around the solar system, things are pretty nicely organized. You don't have planets or oops, hold on a second. alarm went off. That's why I was wondering, Stephen, about well, Mom, where did the other body come from? Or if you look around the solar system, you don't see planets and satellites just wandering around. And if we're creating the solar system to begin with, where did you end up with a body that just is possible, but the probability is very low. The Roche limit would cause accretion problems, and it would have to happen very early on. I mean, if you had something like this, and what happened to the other body? I mean, why don't we see part? I mean, you kind of wonder, well, if another body came in to hit the Earth, why isn't that other body the moon, and why didn't Earth just capture? Well, why do you have to have the secondary happenstance? Much material would be lost to space, of course. And some people, which when I was reading about this, some people say, well, it came from the Pacific Ocean. But, this Pacific Ocean only developed about 200 million years ago or less. And so there's no Pacific Ocean for it to really come from. Another theory is that you had an Earth orbit accretion theory. And this was that there was once a much smaller moon, and it was in orbit around a much smaller Earth, and they both accreted together. This has less problems than either the Barbell or the fission theories, but you have some problems. The Earth and Moon, they were in the same relative environment, but they have different compositions. And the Earth is very heavy in volatiles, and which the moon does not have. And also the Earth has tremendous amounts of iron and heavier metals, which the moon doesn't have. So they're actually, you can't go and compare apples. They have a lot of the same composition because they're in the same relative environment, but there are differences. And where did the embryo moon come from to begin with? This I regard as a less probable subcase of Earth capture. The reason I say that is both the Earth and the moon accreted. So, and that's pretty generally known today or thought of today. And then you end up with the fourth theory, the Earth capture theory. And this is where two protoplanets formed in slightly different orbits about 1 astronomical unit out. Now, that's around the Earth's orbit. Now, there's a fellow by the name of Ernst Oppik, and he analyzed this problem. And Oppik said if you had two bodies, the larger one, the one that started growing larger first, would get bigger and bigger all the time relative to the other one. And he goes into, Oppik was a mathematician and a physicist, and he goes into this in great details. It gets very, mathematical. But the larger one would get most of the metals and volatiles, which the Earth has. And there's no reason if the Earth, and I'm talking in one of Alfvén's, quote, jet streams, where the Earth is forming, there's no reason why you could not have another body form in that same jet stream. Capture is possible on a slow basis, and I'll show you a picture of that. And this explains, and this is one of the big things, this explains the retrograde orbit of the moon and why natural satellites are much smaller in comparison. Now, almost all the satellites in the solar system are prograde. In other words, they rotate in the same direction that the main body planet rotates in. But there's two notable, well, there's like a half a dozen, there's a few smaller, much smaller moons, but there are two huge exceptions to this. One is Triton around Neptune, and one is our moon. And this is, by the way, one of the things with the Barbell theory. If you have these two things rotating around each other, how are you going to get the moon rotating in the opposite direction around the Earth? To me, it doesn't make any sense. And Alfvén's analyses showed that the Earth should have about 5 to 10 moons based on modeling and comparison with other satellite systems. Now, the moon capture mechanism, improbable. It is very improbable that it happened on the first encounter. In other words, we did not grab the moon the first time it came by. First encounter, it changed the moon's orbit, and then other encounters occurred. So once you get in, again, you have the moon coming in, its orbit was modified by the Earth. It went into an orbit, and that orbit would intersect the Earth's orbit twice, two times during the year. And that slowed the moon down until eventually the moon was captured. And they worked out that the probability of this would be very high that capture would occur. I mean, it's kind of a wind down case. And as you're winding down, finally you end up to the place where the moon is captured. Now, here's the satellite system. Here's the sun. Here's all the planets, comparison-wise. And then you take, I mean, these are these satellites, the log of the mass of all the secondary bodies, the satellites, and the log of the mass of the central body. They all fall down, Jupiter, Saturn, Uranus. But then around Neptune, you have Triton. And Triton it falls way out and is also a retrograde orbit. And the same thing with the moon. I mean, it doesn't follow the typical satellite path. And Mars is way down here, but Mars, Alfvén thought there was a very good possibility that the two moons around Mars were probably captured asteroids to begin with. But Triton and the moon are both retrograde, and they're both very, very large bodies, and they don't fall into the regular classification that you would expect for such bodies. Now, something else is accretion is not a cold process. And James brought this to my attention because he said, no, it can't be, because accretion is a cold process and you aren't going to end up with any heat. And he said, I know for sure that certain minerals on the surface of the Earth had to have, that were dated back a long time ago, had to be very, very hot in order to form. But what Alfvén says in Arenas is that the kinetic energy from these collisions create heat. And they estimated that the heat would have, I mean, this is scaleless, but because you really don't know, but they estimated as the Earth accreted more and more, you'd end up with a very, very high level of heat on the surface of the Earth. In other words, it would be almost molten, or could approach that of being molten. And then once the Earth began to cool down and these collisions stopped, you ended up by the heat coming down to what it is today. And there was one other thing I wanted to mention here. Let me see. Bear with me 1 second. No, I forgot what that was. Okay, so anyway, there is a explanation both in terms of the early sun being hotter and also from the standpoint of just the collisions, the kinetic energy. It has to, when two things hit together, the energy has to go somewhere and it heats it up. Now, this was, I thought, one of the most interesting things that I had run across. And it was almost by accident. Alfvén, back in, this is in 1942, when he came out with his first, that little, I told you, the little 40-page or whatever it was booklet. He wanted to find the relationships of the major planets and the minor planets. So he worked it out, and it turns out that over here, for Jupiter, Saturn, Uranus, he could kind of get a curve which most of these planets went on. And in other words, there was some kind of method to the madness of all these gaseous planets. Then he went over and started doing the same thing over here to Mercury, Venus, Venus, Earth, Earth, Mars, and mixed. And he ended up some points over like this, and everything seemed to, all the planets seemed to follow, except for this one planet. And that's the Earth. And both in 1942 and in 1954 book, he mentions this specifically. In fact, in the 1942 book, because this shows that the Earth doesn't fit in this relationship if you compare it to Mars and Venus and what have you by the method he was using. This is what he said. As the Earth-Mars dot is the only one which does not fall on either side, on either of the curves, one must seek the cause of this exception. We should expect it to fall on the second curve because Earth and Mars are both inner planets. If we suppose that it does so, and further assume that there is no error on either side in the Q value, which is one of the values he used, or in the mass of Mars, we can calculate the mass of which the Earth ought to be. The mass we find agrees with the mass of our moon. I did the bolding, but he did he did that in italics to emphasize it. What conclusions might be drawn from this is difficult to say. The moon's large mass and large distance from Earth have already shown it is no ordinary satellite. Instead, the Earth and the moon form some kind of a double planet. And I think that this one is, I mean, to me, this is amazing that way back then, he came up with a logical, the Earth doesn't fit how it should be. I think what happened in our jet stream that the Earth was formed in, there were two bodies formed. One was the moon, one was the Earth. The Earth captured the moon, and that's why it's in a retrograde orbit. But it's interesting that you go back and something that he had absolutely no idea of, the concept of an expanding Earth. Yet he finds that the Earth doesn't fall into the category. And, I personally agree that this is a strong point, that the Earth, when it was formed, was much smaller and later expanded. Okay, now I get into some geophysics. Is the Earth expanding? The answer seems to be yes. This brings up two questions. One, what is evidence in favor of expansion? Typo. And what mechanism is causing the expansion? Okay, now this is like a puzzle. If I gave you this puzzle and said, okay, and took all the pieces apart and said, okay, what I want you to do is put it back together, it's going to be a little bit difficult because you don't have too much to work with. However, if I put a picture there, say, oh yeah, now I can see, that here I have the steeple up here, I have a red roof here, and I have a roof over here. Well, all this expansion stuff is just like a puzzle, trying to put things, pieces together. And here we take the same picture, and I look over, first of all, let's look over here. Well, we have two pieces which are expanded. We have part of the figure here and part of it here. And the same thing is over here, we have it even better. We have this bluish or aqua colored figure here, here, and here. Here we have two, we have a shadow up here. In other words, this is the same thing as what your, David Noel says from the standpoint of distribution of trees and fauna around the planet. You end up ore deposits when you do the reconstruction like James did. You end up by being able to explain where there might be ore here and another piece when it fits in, there's ore here. So it fills out the whole thing. So to me, it's almost like filling out a puzzle. Okay, general approaches to evidence. The more unique features we find, the higher level. Now, once again, by unique features, I mean things which are like the fit, this almost incontroversial types of evidence presented. Let's see. Okay, you end up with physical, well, you can, the removal of the oceans was one of the reconstructions done early on. Remove sections of the ocean floor and the continental basis. That's, James did that to show how the oceans did. You have paleomagnetic reconstructions, and James goes into that in great detail. The geodetic, which I was always fascinated by the fact that he found that they were putting in the fudge factor on from satellite data, and where it showed that the Earth was expanding, and they go and say, oh, something is wrong, so we have to put in this fudge factor. And then you end up with mountains, rifts, dikes, trenches, volcanic placement. Those are the physical things that we can look at. Also, there's biological, trees and other plant distributions. As I say with David Noel, there's another thing with Dennis McCarthy, who has done a lot of work there. He has a book called Here There Be Dragons. I don't know whether you've heard of that or not, but it's a fascinating book where he talks about the Pacific Ocean. And then there's fossil information, and of course, dinosaur size information, which I'm sure that you're familiar with, animal evolution data. Okay, that was the first question. And the first question was, is there evidence to show that the Earth has expanded? The second thing is, what causes the Earth expansion? This is where the topic that I got off on, I was most interested in. Well, Kerry had speculations. One, a pulsating Earth, mass increase due to meteor asteroid strain, early core. That was one of the, if you figure it out, if you take the volume of the current Earth, assume that the early Earth was that compressed down, a higher density, you'd have to end up with some density which nothing even approaches. You end up with density of the Earth now is 5, the average of 5.5 or something like that. But you end up with density 50 times as great. And gravitation has changed over time. But here he was talking about the gravitational constant. And once again, I don't know, the mass of everything in the universe has been increasing. Well, these are theoretical concepts, but it seems to me that all of those are far too esoteric. You can talk about them, you can visualize them, the same ways you can visualize the barbell origin of the moon. But to me, they're not, anyone can come up with a theory, but is it backed by actual empirical laboratory experiments? I always have a very, very high regard for any kind of experiments that you can do, and you can extrapolate from the standpoint of doing this. You can imagine anything. I mean, I can imagine a pink elephant the size of a pyramid floating in space. But does that mean that it's physically possible? No, not necessarily. So Alfvén inspired the path to follow. In writing my thesis, I was studying Alfvén's concepts. Why not think of terms of electromagnetic forces rather than gravitational forces? Now, new mass requires protons and electrons. I don't see any way of getting it. Neil Adams said, well, what we have are a photon that comes in that separates into an electron and a positron, and that's how it happened. You don't do it that way. I mean, if you read any about quantum electromagnetics, with quantum QED, quantum electrodynamics, you'll find that you have protons. I mean, in matter, you have split ups of photons into electrons and positrons, and this type of stuff goes on all around us all the time. It's not that. Both are extremely small. This is an important point to get in mind. A nanometer is about a billionth of a meter. In 1 nanometer, there are 10 angstroms. 10 angstrom is 1/10 of a nanometer. Most atoms are in the range of 1 angstrom, which would be a 10th of a nanometer, to probably 0.7, 0.8 nanometers, 7 or 8 angstroms. So very, very small. Now, the protons and electrons are like 1/10,000th that size. And they're everywhere. Electron conduction occurs, and when I was doing this, I said, why not proton conduction? And so then I started doing a little research, and yes, it does occur, especially like ice and water are excellent. It also occurs in minerals that make up the mantle of the Earth. So, and one point I wanted to make is E equals mc squared doesn't mean that energy can condense into matter. Yes, if you take a particle and put energy into it, it becomes more massive. And if you take energy out of it, it becomes less massive, but you just don't have, I mean, you can, for example, take a proton and hit the proton with a sufficient amount of energy that you can split the proton up into a, what am I trying to say? It's possible in certain circumstances that you can have a proton can split the same way. I mean, if a photon has enough energy and splits, it can create a proton. I mean, it's very similar to pair production, but it's done with protons instead. But really, most of the energy that we talk about, the energy from the sun, most of the energy we talk about actually is energy which is released. In other words, fusion releases energy that has been stored up previously. It's not, we don't go around creating a lot of energy, although energy and mass have this equivalent relation, Einstein's relationship. My hypothesis, basically, we know this. We know we live in an electric universe, at least as far as that's my worldview. The sun provides ample source of both protons and electrons. Earth's magnetic field captures these particles. High energy particles are in the ionosphere. You have massive radiation belts surrounding the Earth, which capture particles. The Earth's magnetic field has sufficient force to move charges. And the Earth's rate of expansion, and this is kind of, I came to this a little bit later, but actually you're saying, well, why did the Earth, and this gets back to the diagram I'm sure all of you are familiar with, is James's diagram of the expansion of the Earth. And you wonder why the Earth waited for what would be 4.25 billion years or something, and then all of a sudden start taking off 200 million, 300 million years ago. And you end up with this exponential expansion. And the one thing which I see is the amount of water, the amount of surface water. Because actually, while the Earth was very hot, for the first several billion years, you did not have a lot of water. You did not have a lot of atmosphere. It's only when because a body the size of Mars has a very difficult time hanging onto an atmosphere. So it was only later on that you began to get water on the surface. And I have it's my gut feeling that the Earth's rate of expansion seems to follow the amount of water on the Earth's surface. And also the Earth is like a giant capacitor, of course. Air is the dielectric in between. Capacitor breakdowns occur via lightning. And you get all kinds of protons, electrons, everything when you end up with lightning strikes. But there's actually like a 200 to 300 volt potential between the ground and the ionosphere. You end up having what they call the fair weather current. You end up with charges actually going up. You can't see them, but they actually go up. And for every meter up, you have a different potential on you. It's just a different electrical potential. But with lightning, you end up with like 1.5 billion lightning strikes a year. So you've got currents are flowing everywhere, above, below, in between. The question is, how can the electrons and the protons create new atoms? We've got plenty of the raw material out there. So nuclear fusion is where you have atomic nuclei of lower atomic numbers fuse to form heavier nucleus with the release of energy. A couple of things that are kind of interesting to keep in mind. First, almost 94% of oxygen is only 4 elements: oxygen, iron, silicon, and magnesium. Another 5% is nickel, cadmium, aluminum, and sulfur. So all the other 90, because there are about 98 naturally occurring elements, all the other 90 are less than 1% of the Earth. I mean, I've always thought that was really interesting. And fusion results in lots of energy being released. But to obtain fusion, one must this is what was a bugaboo for the last 60 years in creating cold or nuclear reactors, fusion reactors. You have the Coulomb barrier. And for over 60 years, they've been trying to figure out a way to tap the power of the hydrogen bomb as a clean energy source, but they've all failed due to the overcoming of this Coulomb barrier. Now, a proton is positively charged, as is the atomic nucleus, so they repel one another like two magnets do. The only way to accomplish nuclear fusion was to accelerate a proton to extremely high energy levels. It's called hot fusion, and to actually have them fuse, you have to really push them together with a lot of force. This is hot fusion. But the Coulomb barrier is like a high mountain. Here is your nucleus, and over here you're trying to come in with a proton to go into the nucleus. And the proton, because of electrical charge, this is positively charged, your nucleus is positively charged. Also, your proton is positively charged, and it will repel it. So the only way they thought this would be possible is to take that proton and shoot it basically out of a gun, and make it very, very hot, so it's very fast, and then it could go in here and fuse. And governments have spent billions of dollars, time and time again, trying to do this fusion, but they fail. They did all kinds of schemes to do it. Now, there's one kind of interesting thing I'll mention here, just from the standpoint. Are you familiar with tunneling?
Yes,
Yeah, tunneling is sometimes you can have a barrier, but you can actually, the probability of the particle out here, and this is basically done with electrons, but since this is a potential charge, but with electrons, if there's a certain probability, according to quantum theory, of the position of the electron, and if there's a small probability that the potential is enough, a electron can tunnel right through this. It pop up over here. It's like trying to push on a door and all of a sudden finding yourself on the other side of the door. I just thought that's kind of extraneous, but to what we're talking about. But cold fusion is the attainment of nuclear fusion at room temperatures. And it was very controversial. If you've ever read anything about cold fusion, it's very controversial, but it's been shown experimentally to have occurred in labs worldwide. And for years, for the last 25 years, there have been conferences on cold fusion, because it's actually some products beginning to come out now that I read about, but I'm not positive. There are no generally accepted theoretical mechanisms for this cold fusion. And the way to tell it happens is that you have excessive heat produced and you have byproducts. And this is somewhat interesting. When you do have fusion, you can have, in some reactions, tritium, which is a radioactive isotope, but this only has a half-life of 12.3 years. So that's why it's not found in nature, or very seldom. And then you have helium. Now, helium-3 is 99.999% of all the helium. Helium-4, which can be produced by fusion in nature, only occurs with this percentage. They're both stable, but by taking the ratio, you can tell if you've had possible fusion happening. And what they do, this is a typical cold fusion experiment. And what they had is this is a cylinder. This is a cross section of a cylinder. But what they would do is they would take liquid heavy water, which has deuterium instead of hydrogen in the water. They take heavy water, put it in here. They take a platinum electrode, and then they would have a palladium electrode over here. And they do electrolysis. And with this electrolysis, pretty soon, you begin to end up with this excess heat and other things produced. And I'm not going to go into the detail. This I thought was a very interesting experiment. And transmutation is changing one element to another. And nucleosynthesis is the formation of atoms more complex than the hydrogen atom. And what they found was, and this is one of the charts that was related to that experiment I just showed to you. What they found is, before the experiment, here's the palladium. This was the curve for all elements found. It was very pure. Afterwards, they ended up by having all kinds of different elements formed because of the reaction. And they took care, this has been reported not only by this Minozu from Japan, but also by other people. This thing of transmutations and nucleosynthesis is something which happens when this happens. Now, within the Earth, there are hotspot volcanoes, like in Hawaii and the Galapagos, that have yielded tritium presence and helium ratios much higher by factors of tens to hundreds than do shallower crustal volcanoes. Now, this is from volcanoes that they assume that the lava comes from very deep within the Earth. But in there, they actually ended up with these abnormal values. And also in crater lakes, where the water at the very bottom does not mix with the upper water, it remains unaffected for thousands of years. Analysis has shown the presence of tritium and the high helium ratio is strongly indicative of what would be expected with fusion within the Earth. Now the tritium, remember, the tritium only has 12.3 years half-life. So all of a sudden they're finding this down. These two things to me indicate that there's a very high probability that fusion was going on within the Earth. Now, whether it's, I think the cold fusion would be, if there is fusion going on, it can't be a runaway like the hydrogen bomb. It's got to be something that's small, but the big, I wouldn't say, the question is, how can a proton overcome the Coulomb barrier to get in and do fusion? And this it seems to happen, but it's really pretty much unknown. So in summary, I've covered Alfvén's concepts of the plasma universe, how galaxies are formed by electromagnetic forces, his concept of how the solar system evolved, how our moon was formed as a captured body, touched on some evidence of Earth expansion, and my hypothesis that electrons and protons could explain the mass gain of the Earth resulting in expansion through cold fusion. So there you are.
Well, thank you very much, John.
A little longer than I expected.
Yeah, that's okay. It's very interesting. But I think if you stop sharing the screen, we can see each other now.
Oh.
I think, that's it. We're back again.
Oh, we are?
There we are.
Yes. Let me see. There we go.
Yeah. I can see everybody now. That's it. Yeah, it's interesting. I mean, the Coulomb barrier there. I mean, as it goes into the Earth, we would actually have a high pressure, wouldn't we? So. Well,
I don't think it's to me it's not the pressure. I mean, what you're doing is talking. I mean, when you're talking about an atomic nucleus or a proton, you're talking about such a minutely small. I mean, even if you had pressure of other atoms around you pushing in, you're still talking in like a thousandth or a 5,000th of. In other words, I don't think it's due to pressure on the outside. I think this tunneling phenomena is almost like a tunneling phenomena that is not theoretically understood, but there's something going on there because it's not a macro process. It's a micro or on the atomic levels. So I don't think it's due to the pressure at all.
Yeah, that I know when I read a bit about the electronics of transistors and Zener diodes and whatever.
Yeah.
I mean, a lot of that, as you say, they talk about tunneling, but I must admit, I didn't quite understand what they were saying. So,
well, the best way of viewing tunneling is there's a hill. You're trying to get over the hill, and you can only get over the, I mean, but you're pushing against one side of the hill, and there's a finite probability because of Schrodinger's wave equation of you being on the other side of the hill. And it all depends on how high the hill is. So the height of the hill is the amount of potential, how much potential you have, like electrical, like with electrical current in your home. You have 120 volts or 220 volts, whatever it is. That's the potential. And what they do with like a tunnel diode, they put a voltage on it, which reduces that potential and makes the hill smaller, so that when you're tunneling, I mean, you might be able to, let's say theoretically, you could tunnel 10 foot, but the hill is 30 foot thick. So by putting electrical potential like they do on a diode, by putting the electrical potential, you lower that and you effectively shrink the 30 foot down to 10 foot. Now you have a probability of popping up on the other side. So that's how a tunnel diode works, if that makes any sense. You're by applying a potential, you're changing it. I mean, but it's I don't know whether tunneling would actually, I would imagine that if you had a proton, the proton acts like a wave, the same way as an electron acts like a wave. So you could have a tunneling effect, but I don't know what it is. But there's several theories out there, and different people maintain, well, it has to be this way and it has to be that way and stuff like that. But how it really ends up being, I don't know. I mean, it's
I don't know. Does anybody else have any questions? I think you should all be able to unmute yourself and ask a question if you want. I think if anyone wants to ask any more questions.
Well, I just have a comment or a couple comments.
Yeah.
First, I think John's the plasma theory of the solar wind contributing mass to the Earth is really wonderful, and to my way of thinking, it really solves the mass problem. I've done calculations that the sun, in recent time, the sun emits approximately 1 Earth mass every 100 million years. But in geological time, going back to say 2 billion or 3 billion years, and this is based on lunar rocks, they figured this out. On average, the sun releases 1 Earth mass every 10 million years, or 10 million years. And it's not a question of, well, why would all this mass come into the Earth? The point is, obviously 100% of that 10 million doesn't come into the Earth, which would make the Earth, but enough of it comes into the Earth. And the other important point about the solar wind is that the Earth actually orbits inside the solar atmosphere. Right. We picture the corona and all that as being fairly close to the sun, but actually the corona goes way out. It's just much more rarefied, and there are great images on the web. If you Google it, and you'll see the Earth's in a sea of plasma. Yep. I mean, it's really dense. Well, comparatively dense. It's not a vacuum, in other words. So the mass problem seems to solve. The real problem, though, with expansion is that, and this is the Edwards paper, I think Matthew Edwards recently published about whether it's slow expansion or fast expansion, and he showed that you need a certain amount of energy to cause the Earth to fight against gravity, to move outward, and that's measured in surface heat flow. And you'd need a lot of energy to counteract the gravitational collapse, the pressure of gravitational collapse. Essentially, it's a competition between heat and energy pushing the Earth outward and gravity pushing the Earth inward.
I don't think it's, to me, it's not the heat that's doing it. It's the fact that as you're creating new atoms.
No, I agree. The heat's not doing it. The heat's the expression of it, is the consequence of it. So whatever doing it has to produce heat as a byproduct, and we can measure. That's why I understand. Yes, correct. So what we need is an enormously higher energy during the periods of expansion than we have otherwise, which says to me that the current heat flow, we tend to extrapolate current heat flow back through geological time, and they say, yeah, heat flow was a bit higher in the past and a bit higher, but there has to have been periods when if there were geophysicists around to measure it, the heat flow would have been off the chart. I mean, much higher than it is at present. So that's now the problem, it seems to me, is shifted away from where did the mass come from, which has always been the criticism of expansion, to how does that additional mass get converted into the energy needed to cause the Earth to grow. And and this is where critics will say exotic physics, low energy nuclear reactions, cold fusion, whatever, not proven. And so there's still obviously problems to be solved, but we're that much closer to solving it because we now have a reliable source of mass, and it's the sun.
Right.
And it's the sun's just spewing this stuff out, and we're getting hit by it every day. Go to the high latitudes, you see it up in the sky with aurora. In fact, the outer planets like Saturn and Jupiter show aurora, whereas the planets like Mercury, Mars, Venus, which have practically no magnetic field, they don't have any aurora because they're just essentially inert magnetically or electromagnetically. So this is another thing that makes Earth unique, is that unlike the other rocky planets and the satellites, the moon, the Earth has a pretty strong magnetic field and would thus be a magnet, an attractor for the solar wind.
And when I came up with this concept about 9 years ago or so, what I wanted to do is to have people think outside the box a little bit. In other words, all the stuff that we had been doing up to then, with like all the stuff Carrie talks about and everything, nobody really considered this mass problem. And you can't look at it from the standpoint, it's not a boulder hitting the Earth, but rather just tiny particles. I mean, they're everywhere. Even raindrops have charges on them. I mean, that's why I today went into a lot of the universe building concepts of Alfvén's, because I thought they were, this whole thing, if you look at it from a worldview, that it's electromagnetic with some gravitation rather than gravitation with some electromagnetic. It's mainly the plasmas and the charges and the interactions that you have. And this was to the best of my knowledge, before I came up with this concept, I had never read anything about it. I mean, it's, but it makes, to me, a lot of sense.
Yeah, and the existence of the solar wind is a relatively recent discovery. It's younger than continental drift, much younger. It was in the mid 50s. I can't think of the scientist's name, but they named a space probe after him.
Van Allen?
No, not Van Allen. I can't think of his name. But it's a satellite that's now exploring the sun. It's very close to the sun, and he proposed in like 1955 that the space is not empty, but is full of solar wind, as he called it, and he couldn't get his paper published.
Yeah.
But then they sent Mariner to Venus in 1962, I think, and sure enough, it's full of solar wind.
Yeah.
And suddenly, so it's a relatively recent discovery. I think people don't realize that the concept of the solar wind is a very young idea. It's not much older than, say, plate tectonics, which is, say, 66 or 65. And his theory was 1955, confirmed in 62. So it's roughly the same age. So therefore, plate tectonics has never really dealt with that issue because it was growing in parallel with the whole theory of the solar wind. And now, half a century or more later, we can combine these, two revolutions, the solar wind discovery and continental displacement, Earth expansion, and come up with a grander synthesis, I guess you'd say.
Yeah, no, I noticed there was a recent discovery that on the moon, the solar wind is actually hitting it and forming hydrogen on there, isn't it? So,
Water.
Forming water, yeah.
Yes.
Which is essentially what you're saying, isn't it, John? I think that
right.
the solar wind is hitting us and not only forming water, but
most of the Earth's water has come out of the minerals on the Earth itself. But what I found amazing, I mean, the question is, why would Earth sit around for 4 billion years with, as James would say, with practically no expansion? You know, as relates to the thickness of a human hair, which is probably under. But why would the Earth stay around for 4 billion years without expansion, and all of a sudden expansion take off exponentially? And the only thing which I could think would be significant would be the amount of surface water that we've had, because it was a long time. You know, after you saw that chart that I did with Alfvén, it goes way up, and you know, then all of a sudden after the impact, the accretion stopped, the heat began to come down and came. But before then, before about 2 billion years ago, there wasn't any atmosphere on the Earth. Any water that would go, the water would go up in the atmosphere, be ionized from the sun. The hydrogen would escape, and then we would end up with the oxygen left over. And that's how the atmosphere became so oxygenated. And then you didn't have any surface water. But finally, you got to the place where you began to have surface water. But the surface water has grown and grown, and water, to me, is a fantastic proton conductor as well as electron conductor. And so I, in my mind, kind of equate these two things together. I think that's one of the things that's unique about the Earth. We had this water, but I think that the water is contributes. I mean, the rate of growth, the volume of water, is very similar to the volume that you've seen in the growth of the Earth. Now, the growth of the Earth is not due to water, but from the standpoint of this process of going on and creating new matter, I think that's somewhat proportional to the water. Otherwise, you would have had growth back before we had oceans, which we didn't. So to me, there's a correlation there. But you know, Bill and I were discussing one time the increase of mass, and we were talking about whether it was a core in the mantle. And I said, well, probably in the mantle, because the mantle is the most active, most. I know that's where I think all the action's going. I know where exactly you might end up with this fusion happening. Down at the D double prime layer, which is the core mantle interface, basically, there's a certain bubbling action going on down there. They seismographically detect it. So that's one area that seems to have something going on down there. Now, whether that's the place where something like this is happening, because you have a metal interior of the Earth. If you take a sphere and you put any kind of a charge on it, the charge will go to the outside of the sphere. I mean, it's not going to stay inside because it all repels. But which gets into a whole other concept of mine. But the where in the mantle this is occurring, I really could not tell. But the fact is, we're getting tritium, which only has a short lifetime, and we're seeing the helium, the helium-4 down there, which is very rare in reality. I mean, in naturally occurring. And you're seeing the ratios be. I mean, there's something going on down there, and it's something active. But I do think that this thing, if you have to get your thinking out of big things, you have to start thinking in terms of atoms, you know, protons and electrons, and how, you know, they go together. But even it's fascinating when I've read, once I got thought, well, gee, you know, what's this in this cold fusion? Because I always thought it was a pseudoscience. And once I started reading about it, I mean, and this has been, the United States has put millions of dollars into cold fusion research. So have other countries. And what they do is this phenomena of taking a very pure, like some people use, I think it was nickel electrodes, like 99.99999% pure electrodes. And later on, when they started looking at it, they found all kinds of other elements. I mean, this stuff, something is going on down at that atomic happening. Level. Yeah.
Yeah. I mean, presumably the concept is that like all these protons is actually virtually flowing through us, aren't they? Are they so small?
Well, they're tiny. I mean, you see, okay, I could take to give you some kind of a, let's see, a human hair is about 3 microns in diameter, which is I'm sorry, it's about 200. No, there's 25 microns to the mil, and a human hair is 3 mils. So human hair is about 75 microns, and 75 microns is 75,000 nanometers. Okay. Now, if you go down, if you take like 500 nanometers, that length is about the frequency of green light. So we're talking about extreme. A billionth is a hard concept, but then you take the nanometer and you go down to 1/10,000th of that. You're talking about extremely fine particles. I mean, and you know, whenever you have a capacitor, you have because of the potential across that, you have some leakage current. Okay, but if you take if you go up to the ionosphere and take 200,000 volts, and you take us as 0, that's 200,000 volts. That means that if you have, depending on how high it is, 1 meter, you might have a charge of a volt across that. And anytime you have potential,
that's all pulling these into the Earth. Then that's the concept, is it? That I presume the voltage is pulling all the protons into the Earth. Then,
well, the magnetic field of the Earth pulls them. They attract. You get a lightning storm. I mean, these currents flow. You get a big electrical cloud over the Earth, and all of a sudden you measure the ground potential, and you've got all kinds of electrons coming in, you know, to match out for the ones that are lost in the clouds. And when you get lightning strikes, go ahead, Bill.
Well, I was going to say that you're right. The Earth's magnetic field is absorbing, causing protons to go toward the South Pole, electrons toward the North Pole because of their charges. And the question is, where is the magnet in the Earth? The magnet, it doesn't terminate at the surface. The magnet is actually entirely in the core, and is caused by convection currents in the core. And the other point is that the Earth's mantle is largely perovskite, magnesium silicate, called bridgemanite, and it is unstable at the Earth's surface. It requires very high pressures, but they've recently discovered a naturally occurring sample of it. But perovskite is a wonderful proton conductor, and in fact, fuel cells are based on the perovskite structure. They don't use magnesium silica because that form of perovskite is unstable at the surface. They use other elements, but the important point is the perovskite structure. And what the perovskite structure does is that it very efficiently hands protons off to each other. I mean, very fast. And so it's not just the water and ice and also rocks that are great proton conductors, but the entire Earth mantle is an ideal proton conductor. And so it's naturally going to shoot right through the Earth to the pole. Where's the pole? The outer core. What's just above the outer core? The D double prime layer. where all this action's going on. And so that, and I think James believes also that that's where new masses or new matter is being created, quote unquote, at the d double prime layer. That also happens to be the point of maximum gravitational attraction inside the Earth. If you look at a curve of gravity in the Earth, it maxes out at the d double prime layer and then drops, and it's got to obviously at the very center of the Earth be zero. Gravity has to be, but if you plot gravity in the Earth, the small g gravity, it would slowly increase as you got closer, max out at the d double prime layer at the core mantle boundary, and then quickly drop off toward the center of the Earth. So all these forces are causing the electromagnetic forces and magnetism are causing the protons, the ions, to move in toward the Earth. And then once it's in the Earth, gravity is going to keep this mass right there at the core mantle boundary, and that's where the action has to be happening.
Yeah.
So
the reason why I concentrate on protons is because the diameter of a hydrogen atom, with the electron going around, or the water. Let me take water. Water is about 1 angstrom in diameter. Now you're talking about the protons and electrons. You're talking about a much, much smaller thing. And the water, I mean, you have to be small in order to get conduction. You can get conduction, as you say, Bill. And in fact, I think where James came up with a d double prime layer, I think in my original paper that I wrote back in 2011, that's where I speculated. I think that's we were talking.
Yeah. Well, the other thing is that 95% of the solar wind is protons. The rest is either electrons or very small amount of helium, but 95% is ionized hydrogen, the proton. And that's all a proton is a hydrogen atom without an electron.
Right.
So, the protons are the important ones. Yeah. In terms of mass and in terms of any kind of nuclear fusion going on.
Well, it seems like my concept has begun to get some people to think think small.
Yeah, I think it definitely has. Yeah. I think we finished with all the questions now then? I think we have we? Or...
I guess so. So I could be, Tony can be facing a long night. Bill can be facing a nice afternoon, and I will be facing a nice morning. So
yeah.
Well, I'm in the Eastern Zone. You're in the Central Zone, right?
Right. I'm in Little Rock.
Yeah. So I'm an hour earlier than you, or later than you.
Yes. Yeah. You're quarter to 10.
Right. Yeah. It's 2:45 here. I think
cocktail hour.
I think Carl is in Germany, so it must be about 3:45 there, and it must be, as you say, nearly midnight for Tony.
So,
yeah. So are we happy just to finish it there? No more questions.
Yep.
Thanks very much, you guys.
Yeah. Well,
appreciate your listening.
Yeah, thanks a lot for that, John. That's an excellent talk, and I'm sure it's really helped. It's helped me anyway, sort of understand the concept of how it might get into the Earth, and then it's
like a puzzle. You get the puzzle, and you put the pieces together, and all of a sudden something is aesthetically beautiful to you.
Yeah.
Now, if you're a mathematician, you get something aesthetically beautiful. That doesn't necessarily mean that represents physical reality. But from the standpoint of the other, but I really, Alfvén, in my estimation, that guy could walk on water, because he was talking about plasmas in space way back in the 1940s. I mean, he was really ahead of his time, and it's really interesting. I think I sent you a copy of that book, didn't I?
You did, yes. Very thick book.
Yeah. So. But it's now you see a little bit more about where he's coming from. And I thought that the concept where it comes down and because of the field, it stops and then it pulls off and gets moving, taking some of the sun's momentum. And as it's doing this, centrifugal force takes it down to the equator where you end up with these jet streams which form the planet. It's just so beautiful. It's the most aesthetically beautiful theory that I've run across about solar system formation.
If I could, am I still on here?
Yeah.
Yes.
Yeah. The scientist who discovered the solar wind is named Parker. I just Googled it.
Okay.
His name is Parker. He's still alive. And they named the probe after him. He couldn't get his papers published because I can't remember what silly excuse he was given. But so it's a relatively recent thing.
Yeah, he's trying to rock the boat the same way all of us guys are.
Yeah.
That's it.
Have a good day, guys.
You too. Take care.
Thank
Okay.
you.
Talk to you. And thank you, Stephen.
Thank you.